Alright, in this video we're going to finish up Chapter 2, Section 2, and we're going to pick up here with Example 4, and that is drawing a graph of a piecewise function. I guess there's two ways you could approach this. We could graph both of these functions and then erase the parts we don't need. Or, there's an alternate method, we'll do that one next I guess. The first one here, this is y equals x plus 2. And of course that's going to be a straight line. Y equals mx plus b. Our slope is 1. Our y-intercept is 2. So we could start out by doing the y-intercept and then graphing some points on slope 1. And it's going to go kitty corner through these boxes. So we could draw it like this. Good enough. And I'll switch over to blue for the other function. Y equals 4. Y equals 4, or you could think about that as 0x plus 4. It's a horizontal line. Y-intercept of 4, and it's got no rise, all run. So here we've graphed both the functions, but we don't need all of those functions. So let's see here. The number over here is a critical one. If x is less than or equal to 1, we want to be on the red line. And if x's are greater than 1, we want to be on the blue line. So we can imagine, a blue or a dotted line here at x equals 1. One function will exist to the left of that line. One function will exist to the right of it. Again, for x values less than 1, we want to be on the red line. So we don't want the red line to go past x is 1. So I'm going to erase this part of the red line. I get a little bit of the blue line there too, but that's all right. Get out of there. All right, and if we are greater than 1, we want to be on the blue line. So the blue line is not going to exist to the left of negative 1, or excuse me, positive 1. So I can erase this part of the blue line and fix that up. One more thing we have to look at here is there an or equal to sign? If x is less than or equal to 1, we're on the red line. So here at 1, we are going to have a closed-in circle. And then if x is greater than 1, strictly greater than, we're on the blue line. So there'd be an open circle here. And we got that gap in between the two. So you could, graph both the functions and then erase the part that you don't need. Or another way to do it is start off by looking at this number. At positive 1 is where we make our transition. So you could draw an imaginary dotted line there where you make that transition on the piecewise function. Say, okay, to the left of that line, for numbers less than or equal to 1, I'm going to graph this line x plus 2. So you'd start graphing it the old way, put a y-intercept at positive 2, and your slope would be 1. Up 1 over 1, and then we're right there. So we know we don't want to go any farther. And we'll just do the slope down 1, back 1, and finish that line off. And then you can say, okay, for values greater than 1, I want to be on the line y equals 4. So I'd pick up here at 4, and because it's strictly greater than, open circle, and then we're on the line y equals 4. And I guess we could finish off this one with a less than or equal to means there's going to be a closed circle there. So however you want to do it, go right ahead. And we have a question down here. What's our question? When I graph the function in example 4, here's what I got. Is my graph okay? No, you incorrectly ignored the domain for each piece of the function and graphed each equation as if the domain was negative to positive infinity. Again, so there's the graphs of both functions, but remember this number here, x is greater than 1 or less than or equal to 1, that's where you make the transition or the jump from one piece of the piecewise function to the other. There are some piecewise functions called step functions because their graphs form discontinuous steps. Looks like a staircase here. One such function is called the greatest integer function. And it's denoted by this, which I haven't seen very much before, int of x, the int of x. Or you've seen this before. It almost looks like double absolute value bars, but more like a bracket. That is the greatest integer function. Where that is the greatest integer less than or equal to x. Or think about it as you're rounding down. If you're taking the greatest integer of 1, you round down to 1 because it is a whole number. 1.3, you would also round down to 1. 1.5 would get rounded down to 1. 1.9 would also get rounded down to 1. Don't think about it as rounding up or rounding off. It's always rounding down. Here's some other examples. The greatest integer of 2 is 2. 2.3 you'd also round down to 2. 2.5 round down to 2. 2.9 down to 2. And doesn't look like the book mentions it. Remember, if you are rounding down a negative number, like if you're at negative 1.2, you're going to round that down to the next negative number. You'd round that down to negative 2. If you were at negative 1.9, you would also round that down deeper to the next negative number, negative 2. Okay, and when you're looking at one of these step functions, greatest integer functions, like I said, it looks like a staircase. If you're looking at just the greatest integer of x, you could think about that as greatest integer of x plus 0. So your y-intercept is 0, and that's where the graph starts. Colored in whole circle on the origin, you go over 1 unit, and where there is an open circle, and then you make the step or the jump up to the next step. Start out with a whole number or a closed-in circle, you go across, and then there's an open circle on the other side. And remember, this graph results from everything in between the whole numbers being rounded down to that whole number. The last thing for this video are functions and difference quotients. This is a good lead into one of the early parts of calculus. And you'll see how much algebra is involved in calculus. I've said it before. Calculus is actually very easy. The algebra in calculus can be very difficult. In a future section, we'll begin studying the average rate of change for a function. A ratio called a difference quotient plays an important role in understanding the rate at which a function changes. They call it a difference quotient, difference meaning subtraction, quotient meaning it's going to be a numerator and denominator. It's going to look like a fraction. So we are subtracting in the form of a fraction. It's a difference quotient. So here we have the expression f of quantity x plus h minus f of x all divided by h for all values for which h does not equal 0 is called the difference quotient of the function f. We've done something similar to this when we were evaluating functions, but now we're going to just do a special scenario. And again, this is a lead into a calculus topic. So here's our function. F of x is 2x cubed minus x plus 3. For part A, we're going to find f of x plus h. And then in part B, we're going to plug that into the difference quotient. And the good thing is, once we find x plus h here, we're going to be able to plug it right in for this spot. We'll already have done all this work, and then we'll just subtract the original f of x and divide by h. So the first part here is going to be the hard part. Our function, f of something, is equal to 2 times that something squared minus that something plus 3. I've taken this original f of x, dropped out all the x's, and left the parentheses open as a placeholder. Now for part A, f of x plus h is equal to 2 times quantity x plus h squared minus x plus h plus 3. So let's do a little algebra on this. We're going to have 2 times this quantity. We'll FOIL this out. Well, it's going to be x squared plus 2xh plus h squared. And I won't distribute the negative yet because we still have to distribute the 2. All right, now we'll do our distributing. Distribute the 2 across the parentheses. 2x squared plus 4xh plus 2h squared. Now distribute the negative, minus x plus h, and then plus 3. So here is our f of x plus h. There are no common terms to combine, so we're going to have to leave it just like that. So this is the answer to part A. Now for part B. And again, for part B, the top of the fraction here, we have f of x plus h. So that's going to be all of this stuff we just did all that work on. So let me even color code this to show you where it all comes from. I'll underline this in blue, and I'm just going to copy what I just found here. 2x squared plus 4xh plus 2h squared minus x plus h plus 3. Okay. Now we want to do minus f of x. We want to minus the original function, so I'm going to minus, and when we're subtracting f of x, it is as a quantity. So it's got to be minus parenthesis, and then here's the original f of x, 2x squared minus x plus 3. And this is a great big fraction, all divided by h. So in the numerator, we're going to distribute the negative across this red f of x, combine like terms, and see what happens. So a lot of this is just going to be copying what we have above. Our 2x squared plus 4xh plus 2h squared minus x plus h plus 3. Distribute the negative. Now it's minus 2x squared plus x minus 3. And this is still all divided by h. It's real easy to drop that denominator. So let's see what happens. And if you do enough of these, you'll start to notice a pattern. Leading term, 2x squared, is going to be wiped out by this, negative 2x squared from distributing the negative. We have a positive x that will also wipe out this minus x. We have a plus 3 that is going to take out this minus 3. So let's see what we're left with. Let me give myself a little more room here. I guess we don't need this anymore. Let's see what we're left with in the numerator and then compare that to our denominator. So up top, we have a 4xh plus 2h squared plus h all over h. Ooh, look at that. Everything has an h in it. I've been noticing a lot of misconceptions though of when you can cancel variables in fractions. So let's look at this numerator as a quantity and factor out an h. Here's an h, here's an h squared, here's an h multiplied by x. So we can pull out an h, and then left inside is going to be a 4x plus 2h. Remember, this was an h squared. We factored one of them out. And then remember, when we factor something out in its entirety, this was an h, and we factored it out in its whole. So it's going to be a plus 1 left there as a placeholder. And now it's all divided by h. So now it's a lot more obvious to see that this h will cancel with the denominator h. Or if you're comfortable enough, you know the denominator will wipe out this one in the numerator, knock this down to first power, and take this one out in its entirety. That's a very good spot to lose track of that placeholder 1, though. Because now we see our final answer is right here. 4x plus 2h plus 1. Lot of algebra in there. A lot of algebra. For practice problems, checkpoint 4 and 5, you know, they are sort of out of order. If you want to do 4 first, go right ahead. Graph the piecewise function. For number 5, do the difference quotient, what we just did on this slightly different function right here. So pause the video, try those, and then fire it back up. See how you did. All right, for the first one, the graphing one here, I'm going to just graph the pieces that I need at the time I need them. So I'm looking here at my transition number on the domain, the x-axis. I see we're switching from each piece of the function to the other at -1. So I'm going to, draw a little dotted line here. I know that I'm going to graph one function to the left of this line, the other function to the right of this line. So let's see here. We'll do this one first. Y equals 3. That's just a horizontal line, and that line only exists to the left of -1. So to the left of -1, we're going to be at a y height of 3 here. Ooh, didn't mean to do that. Right here. And because it's less than or equal to, there will be a, I went a little too far. What am I doing? I only wanted to go to the dotted blue line. Here we go. So we're at -1. That's the end of this graph. And it's or equal to, so there will be a closed-in circle there. All right, I guess I'll switch over to black ink. And this graph here, y equals x minus 2. That's a straight line, y-intercept of -2, slope of +1. So I'm going to go down here to -2 on the y-axis. This is the y-intercept, and then my slope is +1. So I'm going to be heading diagonally through the boxes up and to the right. And of course, I got to back up one until I hit the blue line here at x is -1. And because it's strictly greater than in the inequality, that will be an open circle for this line. So we're headed up this way. There we go. There's our piecewise defined function. Checkpoint 5 was a difference quotient, very similar to the one we just did. Again, these are just very algebra intensive, and it's not even very hard algebra. It's foiling and stuff you learned way back in Algebra 1. So f of x is, I'll underline it right here in blue, minus 2 times something squared plus that same something plus 5. And we're going to plug in the familiar x plus h. And an x plus h here. So we have our minus 2. And now I'm going to FOIL this out exactly the same as the last one. So it's going to be an x squared plus 2xh's plus an h squared. And I won't distribute the positive one yet and drop the parentheses. We'll do that on the next step when we distribute this negative 2 is now going to be distributed. Now it is a minus 2x squared, minus 4xh, minus 2h squared, and now I'll distribute a positive 1 or just disregard the parentheses, plus x plus h plus 5. So there is f of x plus h. And I'll label that f of x plus h, because now we're going to use that piece as this chunk of the numerator in our difference quotient. So for part B, we need this again, f of x plus h. So I'm just going to copy it down exactly as is. That's an x. Now to finish the numerator of the difference quotient, we're going to minus f of x. So minus the original function f of x. Don't forget we are subtracting it as a quantity, so it gets its own set of parentheses. And this is all over h. So instead of copying this all down again, let me just do this. I'm going to distribute the negative here. That will become a positive. I'll distribute the negative. Now this is a minus. And also distribute the negative to the positive 5. Now this is also a minus. So let's see if I can just do, that'll work. Get rid of that. Whoa. And we can disregard the parenthesis, and this minus has been distributed. So let's collect our like terms. Again, you notice these do always fall into a pattern. Leading term is a minus 2x squared, and there is a plus 2x squared to take it out. We have this constant plus 5, another constant minus 5, take care of each other. Here is a minus x, here is a plus x, they take each other out. And now every term left in the numerator contains an x. Minus 4xh, or an h. Minus 2h squared plus h all over h. Again, just like the last one, we can factor an h out, leaving a minus 4x minus 2h plus 1 in the numerator. Divided by h, h is cancel. So our final answer, B, the difference quotient of this is minus 4x minus 2h plus 1. Okay, a few problems to keep you busy tonight, entertain you for a while. Page 240 and 41. These problems here pay extra attention to the even ones.